right, well, welcome everyone, and thank you for joining us today for the AASHTO TRAC Virtual Showcase. I'm Meg Davis with Bentley Systems, and I'll be your host for today. This virtual showcase is brought to you by Bentley Systems, Michael Baker International, Topo DOT, HDR, HNTB, and Headlight. We'd like to acknowledge our TRAC committee this year, made up of AASHTO members, DOTs, and vendors. And without the work of this combined team, this event would not have been possible. I would like to introduce Julia Smith, who's our AASHTO TRAC program manager.
Hello to everyone today. Thank you for joining us. Due to the AASHTO spring meeting being a virtual event, we were not able to have the bridge competition as we normally would. So instead, this is a showcase of the selected student teams. Of the 33 teams who submitted projects, the 10 that you will see today have been selected by the review committee to present. Congratulations to the teams today that are presenting. We also want to thank and acknowledge our student teams, their teachers, and DOT advisors for all of their hard work and perseverance. Each student will be receiving an e-gift card in the upcoming weeks. Again, a big shout out to our sponsors, Bentley Systems, Michael Baker International, Topo DOT, HDR, HNTB, and Headlight, who have made this showcase possible. And last but not least, a special thank you to Meg Davis with Bentley Systems for organizing and hosting this event. Also to Caitlin Mauser with AASHTO for the wonderful graphics and promotional ads and pieces for the website and social media outlets. Meg, back to you.
All right, I would like to introduce our 7th and 8th grade teams. We have Magnolia Builders, Cyberdean Builders, TBD, and the Bridginators.
We're the Magnolia Builders. The reason behind our design was in class, we learned that the triangle was one of the strongest shapes. We knew going into it that we were going to have a strong structure to hold up all the weight.
In class, we learned about strength to weight ratios, which everything had to be balanced to create a bridge that could withstand pressure and weight.
The Warren Truss bridges uses equilateral triangles to spread out all the weight, and it minimizes all compression and tension forces.
Deciding the type of bridge that we were going to make, breaking down and understanding the whole process of what we needed to complete was an immense challenge.
Bentley was a challenge because there was a lot of options that you could choose from. It was really fun after you figured out how to use the options and how to dimension the elements.
Whenever we were testing our bridges, first we masked our bridges using a triple beam balance scale, and then we placed our bridges on a Pittsco structure tester and applied force to see how much the bridge would hold before it broke. And this is on our last attempt on attempt number 4. If we were to rebuild the bridge, we would redo the bottom joint by gluing it together. Some of the joints broke off too. And then we would also make our top not as heavy by using only diagonal braces instead of X's. And we actually went back in and we removed the X's just using diagonal.
We learned that we needed to make sure that we had everything right and it was all symmetrical so that the bridge would be balanced good enough so it could hold. We also learned that our cuts had to be exact or the bridge wouldn't have strength because the joints would not connect. And we learned bigger is not always stronger and taller is not always better when we were building our bridges.
We are the Cyberdean Builders. The reasons behind our design: we used a modified Pratt and Howe bridge because it consists of many triangles. The design was also 2 of the most common designs we've seen so far. So as you can see, the Pratt is on top and the Howe.
With each layer of our bridge being made of different bridge designs, they offset the forces from each other. One of the construction challenges that we faced was making sure that the measurements of the bridge lined up and that one side was not longer retarded than the other. We also had to make sure that the cuts were exact so we would not waste too much wood. Another construction challenge that we faced was having to draw out the design of our bridge as close to the original. It was very difficult to make sure that our bridges were exact copies of each other.
We also decided to use a design on top of our bridge as well. Unlike before, when we had a set of single pieces of wood going across the top. We also noticed that our bridge has two points where the forces meet rather than.
Also, to add on to that testing and improvements, we also had to change up some of the designs. Like, as you can see on this bridge, the top has only singular beams, and we had to change it up by putting an actual design on the top to make it more fortified and change out some of the columns and put them as solid pieces rather than individual cut pieces. We learned that it means to be responsible and working together as a team. We also learned that giving our opinions on any problem and use each other's ideas to solve the problem.
We're the TBD. Starting off with the design, all three of us compared builds and later agreed to use the altered Baltimore truss style bridge. Bridges made of triangles are stronger than those built with straight principles set at 90-degree angles. A bridge has to be symmetrical in order to be strong.
In our Baltimore truss, the design includes diagonal members in a symmetrical pattern that take in both tension and compression forces as the live load processing. By adding vertical supports, the stability and strength of the bridge is increased. Smaller diagonal braces then help to spread out the forces, even making it strong.
During the testing of the K-truss bridge, we saw that the bridge had too much tension. It would not hold much weight. In the end, this is why we decided not to go with the K-12 truss bridge.
As we look at the Baltimore truss bridge design that we chose, we noticed that they all held very well, and the main fault was a construction failure. We mainly favored the structure and design of the bridge along the way it was modified. We then pursued the design.
We learned that one of the most challenging parts of building was attempting to fit the pieces perfectly, as well as being able to have everything symmetrical. Along with this, we learned how to safely use the materials that we needed and to be extra delicate with every piece. Also, having to learn what held whatever better was big necessity. Many triangular pieces were our biggest advantage, especially with the Baltimore truss bridge. We learned that we needed to also pay big attention to all the details.
Hi, we are the bridge leaders. I am John David Hagan,
Colin Krill, and Trey Rock. These are our scientific principles: tension, compression, shear, and torque. This is an example of tension and compression, which is tension, which is pulling the wood tight, compression, which is applying force on the wood, shear, which is sliding the wood, that might cause a structural strain, and torque, which is twisting the wood, that might cause rotation. This is an example of a bridge with torque, which we do not want our bridge to do.
We know that in construction, triangles are the strongest shape because they can hold the most weight. We wanted to stick towards designs like the Pratt, the Howe, the Camelback, and the Warren.
After researching, we tried to decide our design on MonoSmart 2D.
We took our structure weight and our braking load and averaged them out, and these are our top three bridges. John David's best bridge was 1,204. Colin's best bridge was 1,143. And Trey and my best bridge was 896.
This is our best bridge fully drawn out in MonoSmart 2D. This is that same bridge after we analyzed it. The blue is showing compression where it is compressing the wood tight. The green is showing the tension where it is pulling the wood tight. And the red member is the broken member where it broke. This red arrow shows where we put the load on it so we can test it and it'll pour down on the bridge. And over here is a fixed support and a horizontal roller. And the darker shades of the colors mean that it had more strain on the wood. After we had finished tuning both of the sides and doing small tests on them, we had figured out that we needed to rebuild some of the members that were either cracked or broken, replacing weak members because the wood was too spongy, using more glue so it had a stronger fit, and cutting the wood just a hair long so that it would have a tight fit.
This is us after we finished both sides of the bridge in 2D, and as you can see, we finally fixed the 3 pieces of balsa wood that were going the same side.
We measured the mass of our balsa wood because we want to see how much our bridge would weigh and how much we wasted and how much wood we used on. The mass of our bridge was 10.3 grams. The mass of our scrap wood was 3.7 grams. Our scrap wood is the wood that we had put to waste and we didn't use when we were cutting excess wood off. And the mass of one stick is 1.8 grams. We wanted to see how much wood we used, and also we added the mass of the bridge and the scrap wood together and divided it by the mass of one stick, and we got 7.8, so we used about 7.8 sticks of wood in all. We did this because in the real world, when you're doing a real project, you want to be as inexpensive as possible and waste no material.
This is our final bridge design after we 3D'd it, and as you can see where the broken member is in the big red circle, that is where it broke after, in the process of 3D'ing our bridge, it broke. And what we learned from this was teamwork, work ethic, and that when you're engineering, you're going to face challenges and you have to overcome the challenges.
This is our bridge after we had fixed all of the broken members and fixed all of the other cracked members and everything. And this is our bridge now after it was fully built.
Thank you, everyone. And now I'd like to introduce our 9th and 10th grade teams. Our teams this year are Big Brains and Team Volume.
Our team was called the Big Brains. So the goal of this project was to design a lightweight bridge that would hold a lot. So we decided we were going to build 3 separate bridge designs and see which one had the best strength-weight ratio. So we actually ended up all building different variations of the Pratt bridge, and the Pratt bridge originated in 1844, and it was originally designed by Thomas and Caleb Pratt, who designed it to go over a 250-foot gap, and then it was most commonly used for railroads. Some of the complications with the bridge was that we wanted to just keep adding wood to make it stronger, but we needed to keep our strength-weight ratio good, and then we needed to be patient and be precise with our measurements.
The way we design our bridges is with model plane. And the way that you make your bridges is you put the joints on the plane and then you connect them with members. Then you put them about 2 inches apart, connect them across with members.
After we used Model Smart to make our bridges, we made a 2D render in Bentley.
Something I learned from doing the bridge is that when you're building it and you're cutting angles, it's important to get your angles right so there's not gaps in your bridge that are called weak points, and to not force members in that are too long to support.
What I learned was that it takes time, and if there's one mistake, you'll have to rebuild it.
I also learned to be patient with my bridge and allow the bridge to fully dry, and to again be very precise with the measurements and angles.
This is Team Volumes 2021 AASHTO Bridge Competition presentation. I'm Sawyer Levinson. I did a modified Baltimore truss bridge.
And then I did the modified Pennsylvania truss bridge. I did a modified house bridge.
This is my bridge. As you can see, I added and subtracted a couple members from the sides to make it a little bit stronger and weigh a little bit less. My strength to weight ratio was 475.6.
And this is my bridge. It weighed 24 grams and it held 35 pounds. Its length was 18 inches and its height was 4 inches. The strength to weight ratio is 662.1. My bridge was a modified POW. It weighed 19 grams, it held 31 pounds, had a length of 18 inches, a height of 5 inches, and a strength to weight ratio of 740.1. This is the Bentley sketch that we used the Michigan tutorial for to do, and it shows all the different views of the bridge that we chose and all the links.
Possible improvements we could have made were, after making and testing all of the bridges, we could support the ends of the bridges more and put triangles as supports, because we learned that because of Jacob's bridge, the more stuff that you have supporting it underneath, you could still make it light, but also make it strong.
And what we learned patience, and we learned timing, and then we learned craftsmanship, and we also learned teamwork.
Thank you, everyone. And now I'd like to introduce to you our 11th and 12th grade teams. Up North Bridge Builders, Irontown Engineers, Iron Range Engineering, and Irontown Bridge Design Company.
Hello, we are the Up North Bridge Builders of Negaunee, Michigan. I'm Caitlin Lamy, the team captain.
And I'm Lily Ula, and I'm Ella Lunsa. First, we had to learn MicroStation PowerDrive Connect Edition. We had to learn and go over our bridge rules for the competition. We researched and designed a truss bridge. We made drawings for our bridge designs. We had to construct a truss bridge, and then we had to test our bridge. Then we worked on our bridge proposal.
When we first started this project, we researched different types of truss bridges and used those to come up with our own design. After we did that, we researched the scientific principles that are involved in truss bridges, and we found the forces that act on a truss bridge and combated them.
At the beginning of our school year, we did tech talks in class. This helped us practice public speaking, scientific principle research, proposal principles research, and presenting research in class. There are many forces that acted on our bridge while doing this competition, and we tried our best to design a bridge that can combat these forces.
So another force we had to combat was deflection. As you can see, the testing block pushes down onto our bridge, and we had to make sure that our bridge could hold that. In the bottom left-hand corner, we have modulus of elasticity. And that's the pushing and pulling of an object. We have friction, and you can see where our bridge rubbed on the Pittsco tester. And in the bottom middle, we have shear force. And you can see where the testing block pushes down on our bridge and where it would lift up in the back on the other side of the tester. We had different construction tools that we used throughout this process.
Another construction tool that we used was a 3D printer. We used MakerBot Replicator Plus. We used this to make jigs to hold our balsa wood in place while we glued it so it would all be even and so that it wouldn't move. We had many design features that we put into our bridge so that we would have our bridge be the most efficient. We had lightweight zero members, which were single pieces of balsa wood that hold little to no weight. We had heavyweight tower members in our testing block sites, specifically shown in the picture to the right. These were our biggest members because they held the most force. And our double lamination members were the members of two pieces of balsa wood laminated together for slightly more work.
We used different types of software throughout this process. In the top left, we have Model Smart 3D. We used that to create our final design for our bridge. And in the top right-hand corner, we have West Point Bridge Designer. We used that when we started learning about bridges, and we used that to see what we could make. In the bottom right, we have Context Capture. We used that to see how 3D imaging would work. And in the bottom left, we have MicroStation Connect Edition. We used that to make our final design for our final bridge. We used Open Roads Concept Station to see how bridges and roundabouts and intersections work into roadways, and we were able to design some ourselves, which was really nice.
We also did some tests on our balsa wood. Two of the tests that we did were deflection and tensile strength. For our torsion test, we used a protractor to measure the angle that the balsa wood could bend with torsion. For our compression test, we used our Pittsco tester and our testing block to compress two pieces of balsa wood and measure how much compression they can withstand. Here are some pictures of our bridge testing. In the top left corner, you can see what it looked like before there was any weight on it. In the bottom, you can see a picture of what our bridge looked like while there was weight bearing down on it. And then in the top right corner, you can see what our bridge looked like after it broke. The efficiency of our bridge was 84,418.75%, and it held 123 pounds at 66.15 grams.
As you can see, the bottom of our bridge is starting to go down a little bit towards the end, and it ends up causing our bridge to break like that because we didn't have enough support in the bottom.
All right, well, good afternoon. We are the Irontown Engineers. Our team members are Preston Toutant, Ben Helpy, and me, Lucas Nelson. So earlier on in the year, we learned how to pilot drones and submit that into Concept Station and make 3D objects. Next, we learned MicroStation, and we went over the bridge rules to make sure we were all on the same page. We then researched and designed a truss bridge and figured out which kind of truss bridge would work for us best. Next, we made drawings of our bridge. We constructed a prototype, and we tested the prototype. Next, we worked on our bridge proposal.
So to start off the year, we learned how to pilot drones. The two drones we used were the DJI Mavic Air 2 and the Phantom 3. We took footage off the cameras of our school parking lot in our town, and we applied that to context capture. As you can tell here, this is our school, and then going into our parking lot. Then we took that footage and we put it into context captures to try and make our parking lot. So we researched the truss bridge, searched the different designs right away. Then we furthered our search into where the forces get directed. That way we can pick out what's the best one to use for the competition. And then depending on where the forces got directed, we then searched for the scientific principles and how they relate to the bridge. By getting to know the scientific principles, it helped us a lot with getting to put different materials where they needed to go.
So before we started the construction of our bridge, we had to learn about the forces that are acting on our bridge. And these included the compression force that's demonstrated in the red box on the upper left-hand corner, and also the tension force in the blue box in the bottom right-hand corner, and the deflection force. We also looked at the twisting force shown on the bottom right-hand corner, and also the bending force demonstrated on the bottom left-hand corner, and the friction force in the blue box, and the shear force in the red box.
We had a couple of different design features in our truss bridge. we intersected the pieces to make stronger beams. Having the stronger beams puts the force out more onto the tester, and it caused our bridge to hold a lot more weight. And then we intersected the beams to make stronger joints. The joint is where the bridge normally breaks often. So if we beefed up the joints, that caused our bridge to hold a lot more weight and caused our percent efficiency to go up.
We started out with Model Smart 3D and West Point Bridge Designer and tried to create the strongest bridge. And then we went from there building it. We also used Open Roads Concept Station, where we created new roadway systems such as a roundabout and intersections in our town. We also used context capture, where we take a image of an object and create it into a 3D image. We also used MicroStation Connect Edition, shown in the bottom right-hand corner, where we actually drew our bridge. We did multiple tests on our balsa wood. These included the torque test, the density test, and the shear test. We also did a spring force test and a deflection test.
So after we built our prototype, we tested it on the Pittsco tester, and it held 64,041 grams and weighed 85.96 grams. And its percent efficiency was 74,500%. As you can see, it breaks on that left-hand corner along the edge.
Hello, we are Iron Range Engineering. I'm William Rutherford, the team captain.
I'm Dallas Dugley, and I'm Calder Hewitt.
We decided that we wanted to learn how to use MicroStation PowerDraft. We went over the bridge rules thoroughly. We researched truss bridges and scientific principles. We made drawings of the bridge using MicroStation PowerDraft. We constructed a K-truss bridge. We tested the actual balsa wood bridge, and then we completed the 70-page bridge proposal. Another thing that we did was something called Tech Talks, where we would inform the class about advancements in bridge technology and engineering in general. And we learned about current and upcoming bridge designs and concepts, but ultimately, we practiced public speaking.
Some of the research that we did through this project was searching for designs that'd be realistic to make with balsa wood. And we looked into multiple different concepts and designs. We had to find where force would be most effective on our bridge. And we had to look into how all scientific principles would be present in force on our bridge. When designing a bridge, it's important to be aware of how the forces are acting upon it. The first image illustrates how compression forces were acting along the truss of our bridge. The second image illustrates tensile forces acting along the base of our bridge. And the final image shows torsion forces acting upon our bridge. We were able to mitigate the torsion forces by putting crossing members between our two trusses.
Some construction tools that we utilized during our project. Another construction tool that we utilized was MakerBot Replicator Plus 3D printers, which we use for making jigs. In the image to the lower left is what we would call a spacer jig to make interlocking members in our bridge design. To the right is a triangular jig, which we use to make the Ks in our K truss.
Some of the design features which we had were a lightweight bridge deck, which would distribute force from the testing block, laminated members used in trusses, and truss design, which would divert force away from the deck of our bridge. We use software, including Model Smart 3D, West Point Bridge Designer, MicroStation PowerDraft, and Context Capture. We also use Open Roads to put interstates, roundabouts, and bridges around streets in Negaunee, and street lights, traffic lights, and simulated traffic as well. During the construction of our bridge, we performed multiple tests to determine the properties of balsa wood. The first image illustrates us testing how much deflection a single piece of balsa wood can handle. The second image showcases us doing a spring force test. And the third image shows us measuring the differing densities of balsa wood.
During the bridge testing phase of our project, our bridge held a total of 113 pounds while weighing in at 60.93 grams. After using the strength to weight ratio, we found out that our bridge had an efficiency of 84,198%. In this video, our K-truss bridge is shown on the Pittsco tester with the testing block on the roadway. And as you can see, it broke on the edge of the testing block. In this video, drone footage is shown where we captured Negaunee along US 41 with Teal Lake on the left. Good afternoon. We are the Ironton Bridge Design Company. I'm team captain Andrew Faze.
I'm team member Maxwell TRAC.
And I'm team member Braden Oglesby.
First, we learned Microstation Power Draft Connect Edition, which helped us to design and build our bridge. We went over the bridge rules and were introduced into the competition. We researched and designed the truss bridge. We made drawings of that bridge, constructed it, tested it on our class Pittsco tester, and finally worked on the proposal.
At the beginning of the year, we did research on truss bridges so we could find the different design ideas. And then we also researched where the forces are directed in those truss bridges. And doing that, we found the scientific principles that are involved in the function of a truss bridge. So on our bridges, there were some forces. So in the top picture, you'll see the compression force on our bridge while it's on the Pittsco tester. In the lower right picture, you'll see where the tension force is. And then in the lower left picture, you'll see where the torsion forces are on our bridge while it's on the Pittsco tester.
Other forces acting on our bridge include a deflection force between the bottom chord and the load. It would move down when a load was placed on it. The bottom right picture shows a friction force between the tester and the bottom chord of the bridge. And on the left picture, it shows a shear force between the chord and the load on the bridge.
A few different tools were used throughout the construction of our bridge.
We also used 3D printers. Our 3D printers were the MakerBot Replicator Plus models, and they were used to 3D print our jigs. And the jigs were used to make our thicker members of our bridge.
While making our trusses, we used a few different designs for our members. We had our thick compression members, as you see in the bottom picture there. Those members were made thick to hold more force. We had our thin connecting members in the top right photo. Those were just our zero members that held our two trusses together. And we also had our crossing inside piece members, which were the tiny pieces of balsa wood put inside of our 1/2-inch jig there in the top left picture. We also used a bunch of software throughout the unit. The main one was Microstation Connect Edition. This software helped us build our bridge to the best we could. It was very handy. We could see all 4 views of our bridge. And we also used Open Roads. This was a very fun program. We improved roundabouts and intersections throughout our town. We also used context capture. We used this to the best of our ability. West Point Bridge Designer. This helped us see where forces acted on our bridge and made the most cost-efficient bridge. We used Model Smart to see where the forces were on our bridge and which bridge design held the most force.
In the left picture, you'll see us testing deflection by bending a piece of balsa wood to see how far it would deflect before finally breaking. And then in the right picture, you'll see us testing shear force by pulling a piece of balsa wood that's taped to a table to see how much force it could take.
Other tests we did on balsa wood include a torsion test, and compression is shown with red arrows on our bridge in the right image.
In the left image, you'll also see us testing density. We did this so we could find which members would be good in which spots. And then in the right, you'll see us testing spring force by using a spring scale and pulling on a piece of balsa wood.
After the construction of our bridge was finished, we tested on our class Pittsco tester. In the left picture there, you can see our bridge on the Pittsco tester with the testing block slid through the middle of our bridge. In the middle picture, you can see the load is being applied to our bridge and the bottom chord is being deflected. And finally, in the far right picture, you can see our bridge after it was tested. Our bridge held a total of 49 pounds, massing in at 112.36 grams, and our efficiency was 19,798.86%. As you see, Braden is turning the knob, which is applying a force on our bridge. And in the right there, you see our bridge gives out at 49 pounds.
So we have a 2-part question. The first part of the question is, before you participated in this showcase, how many of you were interested in going into a career in civil engineering, working at a DOT? How many of you would have been interested before doing the showcase? And how many of you now after doing the showcase?
I think about 7 or 8 of them are continuing on their education in civil. I can't even express how important this is for the kids and being able to have the opportunity to use Bentley software and all the time that the sponsors put in and really appreciate the opportunities.